Theo Salet, who's currently the Dean of the Department of the Built Environment and a full professor of structural design and concrete structures at the Eindhoven University of Technology. And I found something that I think sounds really cool, which is one of his research focuses, which is numerical concrete. So it is all about the advanced, non-linear, elastic, finite element models of concrete. This is what I had in mind when I was talking about simulating not only load transfer, but also simulating material behavior, simulating the hardening of concrete. But he also works on the integration of design and construction in concrete and the development of parametric design tools. In 1986, he got a master from the Department of the Built Environment at Eindhoven University of Technology, and he went on with his doctoral research on the constructive behavior of foam concrete and in sandwich constructions. He became, after that, a head researcher in structural and material engineering at SGS Intron, and he moved on in 1998 to Wittenfeen and Bols, where he was a project leader and senior constructor and contract manager. Until 2019, Theo Salet is a senior partner at Wittenfeen Bols, and he also got appointed as full professor and dean of the Department of Built Environment. Please have a warm welcome for Theo Salet.
Thank you very much for this kind introduction, and thank you, Harold, for your wonderful talk, because you made life simple for me. I can skip the first slides now. Every talk on digital concrete, I think, should start with the question why. And Harold already answered that question. But I think it's never too late to summarize that briefly again. The first thing is about on construction productivity. There's maybe only one industry that is close to us, and that's not agriculture, as many people think. That's hunting. We shoot as many rabbits as we shoot 50 years ago, and we staple as much bricks today as we did 50 years ago. So that's really a shame. We need to improve on that for many reasons. For instance, to give our kids an affordable house, or to make money as a whole, as society, and save the money for other means than construction industry, for instance, for healthcare or education. The second thing has been discussed as well. It's all about using a lot of materials, and not only the use of materials, but also, for instance, the exhaust of carbon dioxide that comes with it. We make big things, and that's a fact of life. We can't change that, but we need to take the responsibility that comes with it as well. And that particular counts, of course, for concrete, because as you all know, if you make concrete, the cement is there, and you have a byproduct, which is carbon dioxide. By nature, it comes by itself. So it's the cement production that gives that carbon dioxide exhaust, and we really need to fine-tune on that one. It's also about health. That one has not been mentioned. This is really hard work to place the reinforcement bars in their place, but also to be in control of concrete is hard work to do. And it's not always that safe, our industry, if you compare that to other industries. And finally, as has been shown by Harold, is this what we really want, or can we improve on our architectural ideas? To frame that a little bit more different, I will talk a bit about the industry's developments. So first we had the industry 1.0. As we all know, it is just manpower changed by machines who are doing the more physical work for us. The second one is just a line assembly. Let's skip that one. And then the third one, then the robot comes in. I don't think there's a huge difference between the first and the third one. The first one, you have to put fuel inside. It's a burning kind of an engine, and it's a gas oil that you put inside. And here you put electricity in. But nowadays, we put in a lot of our machines, our cars, also electricity. No, that's not the difference. The difference is that one takes bits and bytes. And the difference between taking the bits and bytes really means that from now on, going from mass production, you can go to mass customization. You can make any product that you make unique. And that offers a lot for us as architects, but also for society, for the end users who can select their products now. They become, as an end user, all of a sudden part of the game. And there is an Industry 4.0 that some industries work already on, and that's just connect our printing robots to the environment. That's really the next step. Where are we in our industry? Yeah, we are in Industry 1.0, hey. Yeah? We do have our cranes, and we have a lot of machines to take over the manpower that we had to do in the old days ourselves. We do have some line assembling in our precast industry, and we can do that also in the large-scale civil engineering industry in the same manner. And we can even make our precast elements really high level. So everything has been incorporated here. The architectural facade is already there, the glass paneling and the frames are there. The detailing is made very simple. And that's what we call in the world advanced concrete. If you show that around the world, people say that's really advanced. Everything is incorporated. And the next picture, you have seen that one before. We make this in a hall that looks like this. And this is how we make cars. Yeah? So there's room for improvement, I would say. Yeah? This is the Industry 4.0, some pictures of people who make these drawings, where printers make things, stack things by cranes that are already part of the whole game. They know what to do, etc., etc. But I don't want to focus on that too much. I want to focus on that Industry 3.0 as a starting point with you. Because we are a huge industry, worldwide, and I know that's an odd number. Huh? I add everything up now. It's $10 trillion what we are spending, which is 6% of the global GDP. So we're a huge industry. Yeah? But we're running over time in 20% of our projects, and 80% of our projects cost more than we expected them to cost. And in our industry, in our big industry, there's only a minor percentage of robots at present. So we need to move to a real industry. We need to move to Industry 3.0, not only for us, but for society as a whole, I would say. And we are not the only ones who discovered this. If you look now in all these books of these consultant companies, and you can name them, Boston Consultancy Group or PricewaterhouseCoopers, they all now have found our industry as an interesting industry to make that next step. And this one has been told, it's building information modeling, I think, could be the driver for a success. Why? Because now we have a database. In the beginning, we just made drawings on chalk, and 4 lines didn't know that there were 4 lines, that they together were a window or a slab. But nowadays, if we have 4 lines, it's an object. So we can start to add the data, information to our models, to our drawings. And that process, already mentioned by Harold, I think that's the really interesting thing that we are moving towards. But this is the game changer. So for this, now we have adopted these really BIM tools as information model tools and management tools. Now we're much more in control, and we are really able, I think, to make the next step towards that Industry 3 or 4.0. I focus now on concrete printing. You can do a lot of things. You can work with wood or you can work with plastics, but I focus on concrete printing and on the other technology. Yeah? Not on spraying, but this is the extrusion process of concrete printing. So that's what this talk will be about. It's not new. It's not new. This is a picture from 1933. So this is more than 80 years ago, where people started to work on printing layers in concrete by, yes, a machine. This was Industry 1.0, not 3.0. And I can bring it to life. And you can see what they actually are doing. They pour concrete, and don't put your hand inside, please. There's hammering here and making it smooth. So this is the same story that we just heard. It's just hammering by themselves, but this is a machine. It's just a machine. It's not a robot. This is just a machine doing the same thing. This movie takes 1.5 hours, and when they're ready, they take off the caps and throw them in the air, and that was it. We have never heard anything from them anymore. Until 3 years ago, and I'm making a joke, and I don't want to abuse somebody, but 3 years ago, there was something great news. So 80 years after, a Russian company said, whoa, we have invented something new. Okay, but this is the robot, yeah? So now they changed the machine to a robot. You can feed this with bits, yeah, and bytes. And that makes a difference. The first one could only make one circle. This one can really make mass customized products. And that's the difference between one and the other. But the gap is 80 years. Is it a really good machine? I'm not in a position to discuss good and bad, but you might consider from a construction perspective and an economic perspective that you shouldn't make something small with something big. It's much better to make something big with something small. And this is what a couple of Spanish students did a couple of years ago. They had a machine here and put the machine on top of the printed material itself. So as you can see here, the first layer was printed by a small robot, just a couple of $1,000, I guess. The next one was put on top of that and started to work around, supported by the printed material itself. And the third student had to do something as well, so that machine on vacuum was printing here. It could have done anything, smoothing the surface, adding tiles or whatever. Yeah? And this kind of swarm printing is something maybe to bear in mind if we talk about 3D printing and robots, because maybe the robots that we use are just copies of the robots that come from the other industries. And we simply borrow them because we don't have anything better right now. This was the original idea of Kosnevich, some 20 years ago. Make something big, and the day after you come and everything is finished. What he did is he printed elements, but what he did is he printed layer by layer the elements. Yeah? That's what he did. The alternative came from Enrico Dini, who had the powder bed technology, and there's a powder bed, and then he injected with all the nozzles, the binder material, and layer by layer he built up his own model, as you can see in all kinds of industries with powder bed technologies. And if you blow hard at the end, you have a lot of degree of freedom in your shapes. I think it is really important what Dini did and what Kosnevich did, but maybe this was as important, just a publication of an affordable house of only a couple of $1,000 that could be built in 24 hours. I don't think it's nice, and I don't think it really shocks us from an architectural appealing perspective. But the idea that it could be made by a robot, by a printer, in a short period of time, affordable and mass customized, did attract the attention of society. And what they did in the good tradition, they copied Kosnevich, made inner and outer walls, connected them with a snake like that. Never ever do that, please, because it will always crack here and it will crack there if you put a temperature difference on both sides. But okay, the robot could do that, and they make big blocks and stack the blocks into a wall or print them like that and tumble them over. And by means of that precast technology, block making technology, they made something like this or this or this, and in a way something like that. The alternative has been mentioned as well by Harold. Yeah, that's total custom, and what they do is print on situ, layer by layer, the whole construction of the house at the spot. So it's on-site construction technology. And you might know him from the castle that he printed for his daughter in his backyard. And from that came one to the other. And this is only over the past 3 to 4 years. So we're now coming towards today. This is 3 years ago, this is maybe 2 years ago, this is maybe last year. It's an incredible amount of people working on 3D printing in a way. And that's really fascinating to see how fast this additive manufacturing technology in concrete, in our construction industry, in the built environment, is moving nowadays. This is our machine. So we are one of them. We are one of them and started 4 or 5 years printing concrete by means of extrusion. And that's where I will focus on a little bit now with you in more detail. So we were the stupid ones. We built a big machine to make something small, because we didn't know how to make a small machine at that time. And this one, you can simply buy them from the stock. So this is what we developed, a big machine. There is a facility where we can have a dry mortar. The dry mortar comes in here. Water is added automatically. Then there's a hose. And then the whole machine starts to get in motion by means of our motion controller. That brings this machine into motion, but it's also connected to that one. So everything is connected to each other. It starts with a file, and that file is uploaded to this machine, and that file already contains the shape, so the movement of the robot, but also what happens there in my mixing plant. Everything is controlled within one file up front. And this is how it works, apparently. You just put layers of concrete on top of each other, and you can do it in straight lines or curved lines. It's 2D or a little bit of a texture. I don't want to call that. I still call it 2D. But I think it is a kind of a texture that you bring to your surface because, yeah, you can just rotate every layer a little bit, and then you have a shape like that. We hope to go to that speed. We are not. We started at a speed twice as low as this, and this is now our normal speed. It gives you a little bit of an impression of the speed that we are. We want to double every year, but we don't succeed precisely. So that's how it works. If you go more in depth on the technology, where is the issue? Now, from a technological perspective, the issue is here. If you print too fast, things like this will happen. Just this was supposed to be just a straight column, and it simply tumbles down. As you can see, it's all fresh concrete. If I finish a column of any size, you will see bigger sizes later on, everything that I print is with fresh concrete. It's wet in wet printing, and with that comes the perfect bond between the layers. If you print too slow, which you definitely will have, and this is just an illustration, a poor bond between the layers. So there's a window between not printing too fast, because then this happens, not printing too slow, because then the bond between your layers is not perfect anymore. And that window, fortunately, is pretty large. So we can print concrete that doesn't tumble down. However, we had to find out how fast it is. When does this happen, and why does this happen? So now the research part came in. So we need to study not only the properties of hardened concrete, as we do on cubes and cylinders with compression tests, but we also had to figure out the properties of our fresh concrete. How to do that? Now, we just considered it being mud, soil. So we did compression tests on the soil, sand in here, a sample underneath, a kind of a measuring device here, a load cell to measure the force coming from the sand, and a displacement. This is in compression, this is in shear. I don't want to go too much in detail, but for the structural engineers amongst you, if I have compression and I have shear, I can make a more Coulomb kind of a model as a failure envelope for my concrete. And if I put all of that information into account, it's a really hard work. I have to do two tests, compression and shear, combine the data. So we figured out, let's do a triaxial test, as they do on soil mechanics. You can do everything in one test only, and you can test it on the material as it comes from my hose. You don't have to treat the material up front anymore. And later on, we started to develop something completely different. We said, let's use this kind of a tool that is acoustic, that we do this, and every time, if there's a piece of sound going from one side to the other side, the speed of sound is a measure for the strength of the material. And that's fun, because now we can put that on our robot, we can mount that to our hose, and the concrete that flows out of the hose is tested on the spot. Every couple of seconds it is tested, and based on the speed of sound, the transition of the speed of sound, we know the properties from 1 second to the other second and can be in control of them. Now, once you're in control, we start to make our digital concrete models. Yeah? So this is the same column that you saw previously being printed now, but now in a digital manner. This is my digital twin. The colors are not important. Of course, the force is low here because there's no pressure on site, and the force is high, because the dead weight is on the top. It's not about that, it's about the shape. You can see the same buckling shape. The column that you saw previously is not failing because the wet concrete is not strong enough. The concrete was just failing because it buckled. It is an instability problem. It's just a structural problem that comes with stiffness, not with strength, and with shapes. And that's the funny part, because now I can play with my concrete, which is really an advanced type of concrete, these printable concretes, but I can also play as an architect, as a structural engineer, with shapes to prevent the buckling of this. And once you understand the whole phenomena, you can just print. Now, of course, I made use of the knowledge. I printed the wall with a series of curves that's much more stable in terms of stability, structural stability, and then you can print as high as you want. So if you know the trick, you can just print. You can print fast, and then you're in control of what you're doing. But important is, the message is here, everything is embedded. So the structural analysis of how to print and how fast I can print and information on the bond between layers, it's all embedded. So it is already inclusive in your file, and it's not something that you do separate anymore. Okay. Once we were in control of just printing concrete, our next step was to reinforce it. So this is the next step what we did. Test reinforcement systems. Because if we want to make things structural, and I'm a structural engineer, we need to reinforce the concrete. Without the reinforcement, it's not useless, but the use is limited. So the first thing that we did is just keep it simple. Use traditional reinforcement bars and just place them manually. The first one we did with a robot, and then the other 99 we did with the students, of course. We placed them manually in between the layers and just printed on top of the layers, really simple as you saw in the previous presentation of Harold as well. And then made a kind of a girdle like that. And when we finished it, we had a look on the bond, and then we noticed that if you have these very shape-stable concretes, you have a bit of a problem, because if you push the bar inside, it leaves the red holes there, and if you put the bar on the top, it leaves like a blanket, the holes over there. You can see it here, what's happening. It's really a shape-stable concrete. So that comes with these problems, as you can see here at the bottom pictures. So these holes there, that's not good for durability reasons, of course. You can solve it, but now you have to tweak really and go deep into your material properties of your concrete and make it a high-performance concrete. I will not discuss that in detail today, only show you that it was possible to finish a kind of a girder, and if you have a series of them and put a roof on the top, you have a small kind of a bridge. The second attempt that we did, we changed the game, so let's make it in one process. So instead of having the reinforcement separate, we had a huge bunch of wire, and this was just 1 millimeter, but you can extend that dimension slightly more. And then incorporate that in the filaments. And it goes like that. So the machine, this is a prototype version, so it's unwinding here, and the wire goes with a certain speed that is aligned with the speed of spinning, of course, and then disappears in the filaments. Now, if you have one wire, that's fun, but it's below the minimum reinforcement content, so we add 2 wires, 3 wires, 4 wires, and then you need to be in control, because if you go around the corner, one wire has to move faster than the other, so it becomes mechatronics. That's the issue at that time. So we used that, and with that we made columns like this with the wire that we printed, and then we wanted to use them for reasons of confinement only. So if you compress this as a, see this as a bridge that is compressed in that direction with a wire surrounding like that. For me it was just confinement. It gives me, as a structural engineer, a bit more safety that if I compress unreinforced concrete, so use that in as pre-stressed printed concrete, that wire gives me a nice feeling because everything is embedded and closed within the wire. That was the reasoning that I did this. But to my surprise, it also worked in the beam as a reinforcement wire. Have a close-up look, you can see there is a crack, there's my compression zone, and it simply works as reinforcement as well. That came to me as a surprise. I never intended to do that. The second step that we did, or the third step, is we started to embed fibers. We had to select how to bring the fibers to our nozzle, and after a while we had a kind of a beta version of a machine that we called Fred, that embeds the fibers into our concrete. And the funny thing is, we are now able to embed the big ones and the small ones. They can be made out of steel or they can be made out of glass, it doesn't matter. So any kind of fibers with any kind of grading, just a couple or a lot, or maybe even different types, can now be embedded in the mortar and in the filaments. But do realize, only in the filaments, not in between. But you can sprinkle in between. So if you print, during printing, you can just sprinkle up front or at the back of your nozzle and bring fibers in the interface at the same time. Yeah? So there is an option to have fibers everywhere, in your filaments and in between your filaments. And we tested that, of course. And now my big trick with numerical concrete comes in, because what fiber I should use, I don't know. There are so many fibers, so many concretes. So what we do is have numerical models to pull fibers out of concrete. And by that we can see what shape of fiber, what composition of fiber, what material property of fiber with the concrete fits the best. So that's why we test that before we start to do our experimental test. Now, there was one student who said, but if you print in this direction and you place a filament and all these fibers come, they will be aligned. And he's correct. These fibers are aligned so far, at least with us. So he tried to do, if he could orient them in a certain manner. So he made a magnetic field, so a coil with copper wire, electric feeding on top of that, and then the concrete in here and drag the concrete through. And if you see on this small sample with an oil, so this is the coil, and there is a fiber, and the fiber in the oil is now rotating. Now we did the same trick. We put the fibers in the concrete, pulled them through, and they were orienting the other way around. Yeah, I had some problems, but we started to attach that to our nozzle, and now two things happen. If the voltage is too low, nothing happens, and if we put the voltage higher, all fibers immediately flow out. Maybe I come back next time, and I'm not in control at all on this topic. Okay, based on what we knew, we could print concrete, we can reinforce, we can work with fibers, but we can't orient them. We started to work on the next steps and make some real projects. And that's what I want to finish my presentation with. So the first thing we did is we made a very ugly bridge, and a very small bridge. It is not even a river. Yeah? And the bridge was just, we print a series of elements, and then we use the openings that we have to pre-stress the bridge. And that's all. It's just a pre-stressed bridge. We don't even have the guts to put the parapet on the bridge itself. It was just supported on the supports there and on the left and on the right-hand side. Now, then we started to do material tests. The next step was we did some tests on scale elements. This is not a real size. But on a scale element in the lab by pre-stressing, see how it behaved. And we expected it to behave like just a normal pre-stressed concrete bridge. And it does. This is just concrete bridge. You don't need new coats. This is just concrete that is pre-stressed. You need new coats to determine the material properties because they don't fit. You can't pour them in a mold or a cylinder to test them in compression. That's not possible. But this behaves like a normal bridge. It's just concrete at the end. Okay, when we knew that it worked, we started to print the real one, 3.5 meter span, so it's approximately a meter of height. And then we printed elements. And we printed the elements just for a height like that because our lift capacity in the laboratory is limited. Otherwise, we could have printed 2 meter high elements. And as you can see, the wiring system is embedded there. So every layer is embedded. So if I pre-stress in the vertical direction here, if I pre-stress the bridge, I know at least there's a wire as a kind of a stirrup acting around for reasons of confinement. Now, then we brought the elements to the side. We can stack them together here. And this, for the first time, it was our small and ugly but printed bridge. So as a proof of concept, and as you can see, you can't hardly call it a river. But okay. Then we tested it for the third time. Why did we do that? Because we did not know if during construction we made mistakes. We totally don't have any information on our control of the production on such a large scale. So for that reason, we did a kind of a diagnostic test, not ruining the bridge anymore, but loading it and see if its behavior was in line with what we tested in the laboratory. And there's the bridge. Yeah. Then we thought, this is an ugly bridge, can we move from that? And the word has been mentioned. We started to work on topology optimization, started to work on, can we just place the material where we need it? And let the flow of force tell us where we have to place the material and shape the bridge more nicely and in line with its structural behavior to minimize the amount of material that we need. So this is what we did. We made models, which is a bit difficult because concrete in tension and compression need to be treated different now in these optimization software. And from that, we started to work with our Ministry of Public Works on a bit bigger bridge, a 30 meter span bridge that looks like this. I show you this part here. That part we printed already in the lab, and we tested that. So you see all kind of shapes, similar to the first bridge I showed you, stacked together here in a very industry 1.0 or 0.0 manner. And then we made our first element, and we tested, lift the element, and tested the element completely on its structural performance. And it was a success. The bridge has been printed completely now, all the 30 meters, and it will be assembled early next year. I think it will be ready by February or March, and then can open the bridge, I expect. The next step is housing, and I can tell you it's much more difficult. We launched this program, I think, 2 years ago, and are still working hard to get it finished by this summer. I think we will. So I think by this summer the houses definitely will be there. But it took much more time. It was not the printing itself. The printing itself is quite easy. The problem here is we wanted to print with a permit. We wanted to print with the industry together. We wanted to make a file where everything was embedded. And we didn't want to just make a house as a university. And that makes it really, really difficult to do. We have to learn. All of us, academia, industry, government agencies, had to learn a lot. And we decided to go through that process. So we had to redesign a house, not print a house that is designed based on the design ideas of the last 100 years, but redesign according to the rules of the printer. We needed to learn that, and it took much more time than we expected it. But it came with very simple and different detailing than we had up front. Then we made a mock-up, as you can see here in the lab. Different mock-ups we made on a 1-to-1 scale, testing whatever you wanted to test, structural test, testing with all the detailing, testing with all the MRP services that we had to incorporate. Everything was tested, and I think we will be able to finish this work in January and start do the construction work of the first house in next February. And it took much more time, but now it is an effort of all of us. It's sandwich elements that we have chosen to make. They're tested to all kind of ways. And this is what we actually did. We just made a parametric design with all parties involved. That's us as academia, that's the structural engineer, the architect, that's even the municipality that has to give the permit, and embedded all the information that we needed for the printing and for the permitting and for the construction at the site into one file. And that file is being used, it's sliced, and then from the slicing comes the printing part, as you can imagine. But everything is already there, including the placement at the site of the different components. And, with a big hug between the robot and man, I would like to end this presentation. Thank you very much.
Thank you very much, Theo Salet, for giving us this broad overview. You gave us an historic context, where that all comes from. You also showed the challenges that you have in your research, and you give us an outlook into the future and the challenges of transferring research into industry. So thank you very much. Okay. And the floor is open for questions. And we have one mic here, and it helps for the video stream if you use that.
So you, at a certain point you wanted to 3D print one of the houses on site and not do it as a precast. Is that still the idea?
Hendrik, yeah, it's still the idea, but not the first one. It took us really so much time, and I want to be frank on that, so that everybody, if you have the same experience, you recognize it's not you, it's us as well. It took us that long to make a new design that can be printed and not mimicking or copying the existing things, that we decided to do the first house as a precast element, and the second and the third we will see if we can print on the side. Yeah, so that's we have 5 houses, so we want to make it a learning curve from there. Yeah.
Okay, thank you.
Can you have an idea of printing the speed?
The speed? Yes. Yeah, at present for us is now 20 centimeters per second. But that's just the speed that we use in our laboratory, because we want to keep everything constant. If you start to change, everything starts to change. So we are academia, so I think it can be a bit faster than this. But at the present, it's 20 centimeters a second.
Thanks for your talk. On speed, you were talking about having problems when it's too fast, too slow. Is the speed limited to like the time between layers rather than the movement of the deposition? Or like could you speed up the movement of the arm and just do longer bits, but it's the time between them that's the critical thing?
No, actually, the critical thing is that at the end you work with fresh mortar, so you shouldn't tumble down. So you can print as fast as you want, but then your mortar has to accelerate faster. So it's just a tweaking between a fast hardening mortar that it needs, because if you print with my concrete, it takes 3 hours to harden. So it's really mud. By the time I'm up there, I can just grab the concrete out at the bottom. If I increase my speed, it will go wrong at some point in time. But then what I can do, I can tweak my concrete again, make it such that I can print with a higher speed indeed. So the robot and the technology can print much faster than we do. That's not the issue. The issue is that we need to tweak the concrete to the speed of printing. So it's the material technology that has to meet the speed of printing now. That's where we have to work on. And I don't work on that. I work more on the structural part. So for me, it's fine if I print with 20 centimeters a second. Yeah? But I think others, material scientists, should work on the control of the mortars to print faster. And if you print too slow, then take care of the bond. If you're really fast hardening material and you print too slow, yeah, then the bond between the layers is poor. And you're ruining more or less your material by yourself. It's just a development.
Thank you.
Thank you very much for the inspiring lecture. A question about the Bridge 2.0, as you called it, the joint cooperation with Rijkswaterstaat. What will be the location of the bridge?
Nijmegen. Yeah. I can give you more details. Yeah. And a sneak preview, we might be working on a second one. So also in Nijmegen. Yeah. And it's good to work with one municipality so that you can learn with them and go through this process.